In-class activity 4B, modeling cell phone signals. Cell phones use frequency modulation, FM, to transmit information that a receiving phone uses to replicate the sound of one's voice. Frequency modulation is the repeated shifting of the frequency of a cell phone signal from its base frequency to a slightly higher or lower frequency. For example, to transmit one small bit of information, a cell phone might switch from a signal with a frequency of 1700 gigahertz to one with a frequency of 1700.03 gigahertz. Number one, without doing any calculations, which signal has a shorter period? Well, the shorter period would be the 1700.03 gigahertz signal, and that has a shorter period since there's an inverse relationship between period and frequency. As the frequency increases, the period decreases, and vice versa. Objectives for the activity: you will understand that a sine function can be used to model cell phone signals. You will be able to write equations that model cell phone signals with given frequencies. Graph the functions that represent these signals. Cell phone carriers in the United States and Canada use a variety of frequencies in the UHF band to transmit their signals. These frequencies depend on the carrier that provides the cell phone service. This activity will model a cell phone signal by its power. P of t equals A times sine of 2 pi ft. A is the amplitude, F is the frequency, T is the time since the call was connected, P of t is the power of the signal measured in watts. 2, the cell phone carrier Mobiphone uses a signal with a base frequency of 850 megahertz. Part A, write the equation for the power of the Mobiphone carrier signal if the amplitude is equal to 0.3. Well, we can write this as P of t is equal to 0.3 and then times the sine of 2 times pi times 8.5 times 10 to the 8th power times t. Part B. Let's scroll this here. It's not scrolling, so let's try this here. Part B. What is the period of the signal in seconds? What is the period in nanoseconds? Well, the period is going to be 1 over the frequency, which is 1 over 850 times 10 to the 6, which is equal to 1.18 times 10 to the negative 9 seconds. Or we could call this 1.18 nanoseconds. Part C, using what you know about the amplitude and period, sketch a graph of the signal's power, P of t, on the axes shown. Note that the time scale is given in nanoseconds. All right, so we're going to start here at the origin. I'm going to get my points where the graph crosses the axis, the x-axis, and just mark those. And then we'll mark the high and low points. So between the first 2 points, we're going to go up to 0.3. And then between the next two, the second and third, we're going to go down to negative 0.3. And let's see, right about there. And then just continuing this across like this. And I'm going to connect this with a smooth curve here. There we go. Part 3, a different carrier, telecell, uses a signal with a base frequency of 1900 megahertz, and its signal begins broadcasting at the same time as Mobiphones. Part A, without plotting the signal's power or performing any calculations, which carrier signal has a longer period? Well, Mobiphones signal has a longer period. Part B, without plotting the signal's power or performing any calculations, which carrier signal reaches its maximum value or peak more quickly, mobiphone or telecell? Well, here, telecell's signal reaches its max value more quickly. So here we go. Signal reaches its max value more quickly. Part C. Let's scroll these screens up again. Part C, write the equation for P of T for telecell's signal, then plot both carriers' signal on the set of axes used in question 2, part C. So for part C, we're going to write, 1 second, it's not moving. All right, so this is part C. I'm going to scroll this down a bit, make that a little bit larger. So we can see the graph here, and I can write underneath of this. So let's write P of T is equal to 0.3 the sine of 2 pi times 1.9 times 10 to the 9 times t. The frequency for telecell signal is 1900 megahertz. So let's say frequency for, this is telecell signal. 1900 megahertz. And this is going to equal 1900 times 10 to the 6 hertz, which equals 1.9 times 10 to the 9 hertz. So the period, let's see, is going to be 1 over the frequency. So we get 1 over 1.9 times 10 to the 9, and that's about 5.26 times 10 to the negative 10 seconds, which we could write as 0.526 times 10 to the negative 9 seconds, which is about 0.53 nanoseconds. All right, so let's go back to the graph. I'm going to recreate that first graph that we drew a few minutes ago. All right, and that is mobiphone. And let me just do a different color here. We'll go to red and draw the next graph. So we're going to start at the same point, and I'm going to get my intercepts here. So I have one about here. Here. Amplitude is going to be the same. So I'm just going to draw a quick sketch of the first one. There we go, this is the first cycle. And then recreate this. There we go. And let's do one more. Okay, let's go to the next question. Question 4. In question 3, you compared mobile phone signal with that of another carrier that uses a higher frequency. Now let's compare a mobile phone with a carrier that uses a lower base frequency. Suppose that the carrier X cell uses a base frequency of 700 megahertz, and its signal begins broadcasting at the same time as mobile phones. Part A, without plotting the signal or performing any calculations, which carrier's signal do you think reaches its max value or peak more quickly? Mobile phone or X cell? So we could say that mobile phone, let's say the signal reaches its max value more quickly. And X cell. And that's since it's a higher frequency signal. That was part A. Let's go to part B. Now plot both carriers' signal on the following set of axes to compare the signals and verify your answers from part A and B. Assume that X cell signal has the same amplitude as that of mobile phone. So again, we have a graph here. Let me just scroll this down, make a little bit more room. And then there's our graph. So let's plot, I'll do mobile phone first, starting here. Just recreating the graph. Again, that is mobile phone. And so we used red before. Let's go. I'll just use green this time. And we're going to start at the same spot here. Cross about here. Out there. Let's see. This is X cell. So if we wanted to write something here, we could say the frequency X cell signal is 700 megahertz, which equals, let's do the equals down here, which equals 700 times 10 to the 6 hertz, which is equal to 7.0 times 10 to the 8 hertz. Therefore, the period is 1 over the frequency, which is 1 over 7.0 times 10 to the 8 to the 8. Let me do a better 8 than that. There we go, 10 to the 8 equals 1.43 times 10 to the negative 9 equals 1.43 nanoseconds. That is the end of this video. Thank you.